In this video, I'm going to show you how to use motion graphs to do calculations for distance time graphs, velocity time graphs, and acceleration time graphs. This is part of the IB Topic 2 syllabus, so it's for HL and SL. Please take a moment and read the success criteria for this video. Okay, so let's start with distance time graphs, the ones that most people are familiar with. I've already done a video on interpreting distance time graphs, so you should be able to see here that at the beginning, since we have a curve in this area here, we are increasing our gradient, so this is acceleration, speeding up, and then it's going to be traveling here at a constant speed, and you can see the gradient of this line is decreasing, so it slows down, and at this point it stops. I've said that this is a toy car that's moving. Okay, so the first part it says calculate the average velocity of the toy car. So for average velocity, it's always just total distance over total time. And you can read off this graph, the last point here is after 40 seconds and 300 meters. So I'm just going to substitute that into our formula. Remember, we can put on here the units as well as the values. That's going to end up giving me 7.5 meters per second. It's important that we do check out whenever we use a graph that we have the appropriate units that are being included. Sometimes, especially in topic 7, they'll have a multiplier there like times 10 to the power 7 or things like that. Also comes up a lot in topic 10. All right, so let me just include this number up here at the top where we've got our question. So now the next part. It says calculate the velocity of the car at 20 seconds. Now in this case, we're looking for the speed right here. Now notice that is in the section here that is moving at a constant velocity. So I can take any 2 points along this section here that's part of the straight line, and I will be able to get the gradient on my distance time graph to give me the constant velocity anywhere where it's a straight line. Now we're going to take 2 points that are easy to read. And remember that the IB expects us to read each graph to the nearest half square. I can't tell you how many times as an examiner I've not been able to give full marks for students who have just assumed that, oh, it's close enough, I'll just round it. And please don't. The other thing is, since we're reading to the nearest half square, we want to choose these points far apart from each other. If you think about it, this distance here is going to be measured. Basically, you're measuring how far the run is and the rise. So when you have 2 points that are very close together, 1/2 square can be a very large percent uncertainty, especially if you have them only 2 or 3 squares apart. So we're going to choose 2 points that are far enough apart, but still easy to read to the nearest half square. Now you take a look. I've chosen the points 1570 and 30,250. They're still part of the straight line segment, but any farther and I would start to get into the curve section. They're also fairly easy to read. So if I want my velocity, I need to calculate my gradient. So on the top, the change in y over the change in x. 250 minus 70 divided by 30, subtract 15. Put that in your calculator and you're going to get 12 meters per second. Now let's think, does that make sense? That's a lot higher than what I calculated for the average velocity. Well, if you think about it, if I calculate the average velocity, that's really just using the first and last point. And you can see I've just drawn this blue line on here. That's actually the gradient you're calculating when you use the first and last point. And that definitely is not as steep as this section here where I have um, where I'm traveling at a constant speed. Let me write that in up above. And now we're down to the last part. Calculate the instantaneous velocity of the toy car. Now what that means is I want to know what's the speed that I would actually read. For example, if I was driving my car, what would the speedometer tell me? It wants to know the speed at that exact moment. Now, in the second part, I was able to calculate the velocity at 20 seconds because it was traveling at a constant speed this whole time. But that's not the case here at 10 seconds. So what I need to be able to do then, I'm just going to get rid of these other lines. What I need to be able to do then is be able to somehow calculate its speed right at this point. So what we're going to need to do then, in order to get the speed, is we're going to calculate the gradient at that point. How are we going to do that? Let's use the tangent of the line to the curve at that point. Now, when you're drawing your tangent, I usually recommend that people draw first the normal. I find that people are better able to now make the tangent, which is going to be perpendicular to the normal, after drawing that. I feel that people are more able to accurately draw a normal than they are a tangent, and it does take some practice. Okay, it's really hard to draw here, but I did this graph on paper and followed my instructions like I just said. And my line went through 60 and 28, 150. Um, every time if you had to do something like this on a exam, what happens is the examiners will go and when they're making the marks or when the principal examiner makes the mark scheme, they actually have a range of what they're going to expect. So you don't have to be perfect, but you have to be pretty close. And if you follow those steps, you should be able to get within rounding distance of what I'm going to calculate. So to get the velocity then at 10 seconds, I'm going to find the gradient, the change in y over the change in x. You can use whatever way your math teacher has told you in the past. I'm going to have 150 minus 0, 28 minus 6, and that's going to give me 6.8 meters per second. Okay, so I hope this has helped you then to be able to calculate velocities, whether it be the average velocity, the velocity at a point where it's going at a constant speed, or an instantaneous velocity when a object is accelerating. One last thing I do want to point out is notice I've written down 6.8, but if you put that in my calculator, there's a lot more decimals. The issue is how accurately can you read your values? And in this case, yes, I've got the value 6 there, but a lot of them have just two significant figures. I can't, for some reason, make my calculator all of a sudden get my measurements to be more accurate than they really are. So please don't go and write something like 1/3 or 3 with a little dot over it, implying it goes on forever and ever. You need to round it and take care with your significant figures. I would never round to less than two significant figures, but if I had a more precise scale, I might actually be able to get 3. Okay, moving on to velocity time graphs. So for my previous video, you should remember that a straight line now is going to imply acceleration and uniform acceleration. Our horizontal line at the top there would be a constant velocity, and the last part is the slowing down. Okay, so on a velocity time graph, if I want acceleration, I need to calculate the gradient. So for the first part, calculate the acceleration of the train in the first 100 seconds. Here we go. And this point here is at 100 seconds and 30 meters per second. Remember what I said earlier about being able to use with units? This ends up giving us 30 meters per second divided by 100 seconds, and so the units are meters per second squared. The next part says calculate the deceleration of the train. And here's where I want to highlight the word deceleration is an everyday English word and not a science word. It does not imply negative acceleration. You can see my other videos for a more detailed explanation of that. In this case, I do want the point though where it's decelerating. All it's saying is where it's slowing down. And that will be from 200 seconds to 300 seconds. Now, in this case, I get negative 0.3 meters per second squared. Actually, let's go fix this because the IB would prefer you to write it as meters s to the minus 2. Now, I said that deceleration isn't necessarily negative, but in this case it is because these are all positive velocities. Now, the last part, calculate the total distance traveled by the train. As you should know from my previous video, in order to get distance traveled on a velocity time graph, I need the area found underneath. Now, here's the thing. I don't ever remember the equation for the trapezoid or trapezium. So what I'm going to do is I'm going to break this into two pieces. Or three pieces, a rectangle and two triangles. So if I want the total distance traveled, I'm going to have the area of the triangle, 1/2 base times height. Don't forget, in the data booklet, there are some mathematical formulas like that for you at the very front. I don't think the triangle and the rectangle are there, but there is for the circle and spheres. So 1/2 times the base, which is 100, times the height, which is 30, plus the area of the rectangle. The length of the base is 100 times the height of being 30. And finally, the triangle 1/2, the base is going to be 100, so that's 300 minus 200. And the height is 30. And all that together is going to give me a value of 6,000 meters. Now, if it was below the x-axis, then we would be talking about it going backwards. And so I would actually subtract that distance from if I'm looking for a displacement. And one more question about relating our time graphs. Sketch the distance time graph, speed time graph, and velocity time graph, acceleration time graph for a free fall object. Ignore air resistance. So let's first of all think about this. So we're going to take a ball and we're just going to let it drop. And I'm going to say up is positive. So what does that mean? Well, let's say it's going to start from a certain distance called height. So let me do my distance time graph here. And it's going to start at height h. And as it falls over time, it's going to speed up. So I'm going to have a curve for showing acceleration. And my curve is going to have to be in such a way that it will increase in gradient. And what will it look like? It will look like this. Okay, now let's do the speed time graph. Well, a speed time graph, it's just going to start at 0 and increase in speed. But a velocity time graph takes into fact that it's a vector and it's moving in a negative direction. Therefore, when it speeds up, yes, it gets a larger magnitude, but it's in a negative direction. So my velocity time graph should actually look like this. And if I took and had the gradient of that, it should be, that's right, 9.81 meters per second squared, because the gradient of a velocity time graph gives me acceleration. And since we're ignoring air resistance this whole time, if I had my acceleration time graph, and since down is negative, my acceleration that whole time then would be negative 9.81 meters per second squared. and it's a constant value, so it would be shown below my x-axis. Okay, so take a look at those success criteria one more time. I hope that this video has shown you examples of being able to do all of these different types of calculations.